Geometry in the Greek-Hellenistic era and late Antiquity.
Triangles, circles, squares. Yeah, we see them everywhere, right. But have you ever really stopped to think where these basic ideas about shape and space came from?
Hmm.
Well, it turns out the foundations, like the real groundwork for geometry as we know it, was laid down thousands of years ago in ancient Greece.
That's exactly right. And getting into this history, it's not just about dusting off old theorems. It's really uncovering a whole way of thinking,
Yeah.
a way that genuinely shaped the world we live in today.
Yeah, absolutely. So today we're doing one of our deep dives. We're going to explore how geometry developed through the Greek Hellenistic times and into late antiquity.
And our guide for this, our sort of map, is a chapter from a textbook. It's
Yeah.
called 5000 Geometry-Arrow2.pdf.
Now, hold on. Don't let textbook put you off. Seriously, this isn't going to be some dry lecture.
No, not at all.
This chapter actually makes the ancient world feel, well, alive. You know, we're talking about seeing diagrams they might have actually drawn.
Yeah, illustrations from their original text.
And even maps showing how, like, geography influenced things. You can see bits of Euclid's Elements, the actual title page from the first English version.
Mm-hmm. And even a page from a Vatican Library manuscript. It's quite visual.
So our mission here isn't just to list definitions. We want to get inside their heads, right? Understand how the ancient Greeks thought about geometry.
Exactly. What sparked their curiosity? What were those real light bulb moments, the big breakthroughs? It's like tracing the roots of a field that's still fundamental to, well, everything from building bridges to understanding the cosmos.
Okay, let's jump in the time machine then, way back. The Ionian era, maybe 600 to 450 BC, early days. What was the vibe like then, intellectually speaking? What got this whole geometry thing started?
Well, what's really fascinating is this general feeling among the Greeks back then. They seemed to believe that the world, natural phenomena, wasn't just chaos.
Right, order.
Yes, order. They believed it followed rules, systems. And this belief, it really fueled this powerful drive to understand those systems, to systematize them, develop logic. That's the fertile ground where scientific mathematics really started to grow.
And this wasn't happening in a vacuum, I assume. Geography, politics, they must have played a part.
Oh, absolutely. Think about it. You had migrations, all these different independent city-states scattered around.
Lots of mixing.
Exactly. And crucial contact with older cultures. Egypt, Mesopotamia. They definitely learned practical stuff, rules of thumb, procedures from them, observation, collecting rules. That was important.
But the Greek twist was...
The shift towards theory. Moving beyond just how to do something, like measure a field, to understanding why it worked, formulating general principles. That was the key innovation.
Okay, so this leads us to someone like Thales of Miletus, around the 7th, 6th centuries BC, one of the first names we can really connect with specific geometric ideas. What's his story?
Well, the accounts are, a bit mixed with legend sometimes, but Thales is generally credited with traveling to Egypt, maybe Babylon, and bringing back geometric know-how to Greece.
Okay.
And several really fundamental results are attributed to him. Things that seem almost obvious now.
Like what?
Like the base angles in an isosceles triangle are equal.
Huh.
Or that vertical angles where two lines cross are equal.
Simple stuff, yeah.
And that a triangle is fixed if you know one side and the two angles next to it. Oh, and that a diameter cuts a circle exactly in half.
Okay, sounds basic. But you're saying these were a big deal then?
Huge deal. Because their real significance is they mark the beginning of deductive reasoning in geometry.
Yeah.
It wasn't just, look, it seems true. It was the start of saying, this is a general principle, and we can logically argue for it. The first tiny steps towards mathematical proof.
Right, the why, not just the what.
Precisely.
And Thales wasn't alone in trying to map things out back then, was he? I think the source mentions Anaximander and Hecataeus too.
Yes, exactly. Also from Miletus. They were pioneers in sort of geographical representation, trying to make sense of the Earth's layout more systematically.
How did they picture it?
Well, Hecataeus, for instance, his map basically showed the Earth as a flat circular disk.
Ah, okay.
Surrounded by this big ocean. Which sounds quaint now, but it shows how geometry was immediately tied to trying to understand their physical world. There's actually a picture of his map concept in the source material.
Interesting. Okay, so from those early Ionian thinkers, we move on to another really famous, maybe slightly weird group, the Pythagorean school, 6th century BC. Sounds almost like a cult sometimes.
It does have that reputation, doesn't it?
It's
a bit secretive. Founded by Pythagoras of Samos. And yeah, it was this blend of mathematics, philosophy, even religious ideas all mixed together.
And their big thing was numbers, right?
Absolutely central. Their core idea, their mantra almost, was all is number.
All is number. That's ambitious. How did that actually play out in their maths?
Well, they got really deep into number theory itself, looking at odd and even numbers, primes, squares, things like that. And they famously connected numbers to music.
Ah, the harmony idea.
Exactly. They believed musical harmonies could be explained by simple ratios of whole numbers, which to them suggested this deep numerical order underlying the whole universe.
And then, of course, the big one, the Pythagorean theorem, the right-angled triangle thing.
The theorem, yeah. A squared plus b squared equals c squared. It's probably their most famous legacy. Now, there's some evidence the Babylonians might have known the relationship earlier,
Okay.
but the Greeks, likely the Pythagoreans, are credited with the formalization and probably the first proper logical proof. It's a cornerstone.
But didn't their number obsession hit a snag? There's that story about irrational numbers.
Ah, yes, the crisis.
Yeah.
Legend has it that one of them, Hippotasis, discovered something deeply unsettling to their worldview. Irrational numbers, meaning numbers that can't be expressed as a simple fraction, a ratio of two whole numbers. He apparently showed this with the diagonal of a square compared to its side.
Right. You can't write that ratio down perfectly as a fraction.
Exactly. This idea of incommensurable magnitudes, it flew right in the face of all is number, at least in terms of whole numbers and their ratios. It supposedly caused a huge uproar, a real philosophical crisis for the school.
Wow. A mathematical bombshell. So after the Pythagoreans, things shift. We get to classical Greece. Athens takes center stage, maybe 450 to 300 BC. What's happening with geometry then?
Athens definitely becomes the new intellectual hotspot.
Yeah.
And a huge influence was Plato's Academy, founded around 387 BC.
Plato, the philosopher.
The very same. And he held mathematics, especially geometry, in incredibly high regard. He saw it as essential training for the mind, for clear, logical, philosophical thinking.
Wasn't there that famous inscription over the door?
That's the one. Let no one ignorant of geometry enter here. It really shows you how much Plato valued abstract reasoning, the world of ideal forms, and geometry was seen as the key to accessing that world.
So geometry becomes almost like philosophical training wheels.
In a way, yes.
Yeah.
It shaped how maths was studied then. And we see other important figures emerge too, like Eudoxus of Cnidus.
What was his contribution?
Eudoxus made really crucial advances with the theory of proportions. And this was vital because it gave mathematicians a rigorous way to handle those pesky irrational numbers, the incommensurables that bothered the Pythagoreans.
So he found a way to work with them mathematically.
Pretty much. His work provided a solid foundation for dealing with these magnitudes, and it massively influenced Euclid later on.
Okay. The source also talks about these three classical problems of antiquity. Sounds intriguing. What were they trying to solve?
Ah, yes, the big three. They were these geometric construction challenges that obsessed Greek mathematicians for ages. First, doubling the cube, basically, making a cube with exactly twice the volume of another one. Second, trisecting the angle, dividing any angle into three perfectly equal parts. And third, squaring the circle, drawing a square that has the exact same area as a given circle.
Sounds tricky. What was the catch?
The catch was the tools you were allowed to use. Only an unmarked straight edge and a compass. That's it.
See, could they do it?
Well, ultimately, no. It was proven much, much later that all three problems are actually impossible using only those tools.
Huh. So they spent centuries on impossible problems.
They did. But it wasn't wasted effort. Trying to solve them led to loads of mathematical innovation. For example, someone named Hippocrates Chios worked on squaring lunes, these crescent shapes, which was related to squaring the circle.
Oh, okay.
In the study of conic sections, slicing cones to get circles, ellipses, parabolas, hyperbolas, that might have started with Menaechmus trying to solve the cube doubling problem.
Right. So the attempts themselves were productive. Which brings us, I guess, to the giant of geometry, Euclid, around 300 BC. In his book, The Elements...
Oh, giant is right. Monumental is the word often used for the elements. And it fits. It wasn't just a collection of facts. It was this incredibly comprehensive, logically structured presentation of pretty much all the geometry they knew.
So he gathered everything together.
He built on earlier work, definitely. But his genius was putting it all into this rigorous, axiomatic framework.
Axiomatic framework. What does that mean, practically?
It means starting right at the beginning, with basic definitions, what's a point, what's a line, then postulates things you accept as true without proof, like you could draw a straight line between any 2 points, and common notions, general logical truths.
Like building blocks.
Exactly. And from that solid foundation, he used deductive logic, step by step, to prove theorem after theorem, hundreds of them. It's this logical structure that made the elements so incredibly powerful and long-lasting.
And it was a big work, 13 books, I think.
That's right, 13 books, covering everything from basic plane geometry, triangles and circles, up to solid geometry, 3D shapes, and even number theory. And its influence, it's hard to overstate. It was the geometry textbook for over 2,000 years. Across cultures, across continents, our source material shows this incredible history bits of ancient papyrus copies, that first English translation from 1570, the Vatican manuscript. It just endured.
It's wild to think a book from 300 BC was the standard for so long. Was it ever challenged? Did people ever question Euclid?
Oh, definitely. Over the centuries, mathematicians did scrutinize it. Some found the definitions a bit vague, or questioned if all the postulates were truly self-evident.
Any famous examples?
The most famous is the parallel postulate, the one about parallel lines. Questioning that postulate eventually, much later in the 19th century, led to the discovery of completely new types of geometry, non-Euclidean geometries, which really changed how we think about space itself.
Fascinating. Okay, so after Euclid's era, the focus shifts again, right? To Alexandria in Egypt, the Hellenistic period after Alexander the Great.
Exactly. Alexandria becomes this major powerhouse of learning, of science, a real magnet for brilliant minds. And this period sees some absolutely stellar advancements in geometry. We're talking Archimedes, Apollonius, Eratosthenes, giant.
Archimedes. Everyone knows Archimedes, Eureka and all that.
Yeah.
What were his big geometric contributions?
Archimedes was just a genius. On another level, in geometry, he developed these incredibly sophisticated methods for calculating areas and volumes, things that were really precursors to calculus.
Like the method of exhaustion.
Precisely. He used it to find the area of parabolic segments, the volume of spheres. He also got incredibly close calculating the value of pi.
Wow.
And he wasn't just theoretical. Mechanics, hydrostatics. His work on the sphere and cylinder is a classic. He studied spirals, too. The source even has that fun, probably legendary illustration of him using mirrors to burn Roman ships.
Huh. Yeah, I saw that. And there's a page from the Archimedes palimpsest too, right? And something called a Stomachian puzzle.
The palimpsest gives us insight into his lost works. And the Stomachian was this geometric dissection puzzle he analyzed. Shows the breadth of his interests.
Okay, amazing. Then there's Apollonius of Perga. He's the conic sections guy.
He is. His work on conic sections, the ellipse, parabola, hyperbola, was absolutely definitive. He gave them the names we still use.
So he really mapped out their properties.
Thoroughly. His treatise on conics was incredibly detailed and rigorous, hugely influential later on, especially in astronomy. Think Kepler's laws of planetary motion, which involve ellipses.
Right, right. And the third name you mentioned from that era was Eratosthenes.
Eratosthenes of Cyrene. He's famous for that amazing calculation of the Earth's circumference.
How did he even do that back then?
He was incredibly clever. He used the difference in the angle of the sun's rays at noon in two different cities on the same day, plus the distance between the cities. Basic geometry and observation, but applied brilliantly to figure out the size of the whole planet. Remarkably accurate, too.
That's just astounding. A real testament to the power of this geometric thinking.
Absolutely. It shows how geometry wasn't just abstract shapes. It was a tool for understanding the real physical world.
So the Hellenistic period was clearly a high point. What happens next as we move into late antiquity? Rome rises, then the Byzantine Empire. Does geometry change focus again?
Yeah, there's a bit of a shift. You see, maybe more emphasis on practical applications. Things like surveying, astronomy, map making become more prominent.
Okay. Any key figures from this later period we should know about?
Well, there's Heron of Alexandria, around the 1st century AD. He came up with that really neat formula for a triangle's area, just using the lengths of its sides, no angles needed. Our source has a page from his book, Metrica.
Useful.
Then Claudius Ptolemy, 2nd century AD, hugely important for astronomy and cartography. His book, The Almagest, was the standard astronomical text for like 1,400 years, and it relied heavily on geometry, especially trigonometry, using chords in a circle. There's a diagram in the source showing that chord-sign relationship.
Wow, another long-lasting text. Anyone else?
Pappus of Alexandria, around the 4th century AD. He was important as a commentator and synthesizer. He wrote collections that summarized and extended a lot of the earlier Greek geometry, preserving knowledge.
And the Romans, we think of them more as engineers, builders. Did they use geometry much?
Oh, definitely. Maybe less focus on pure theory. But geometry was crucial for their engineering, their architecture, and especially their surveying. They had professional land surveyors called agromensors.
What did they do?
They used geometric principles and tools. The source shows one called agroma for setting right angles to lay out roads, aqueducts, city grids, boundaries. Very practical stuff. There's even a manuscript page shown from these surveyors with diagrams and definitions.
So geometry was baked into the infrastructure.
Pretty much. And the tradition didn't completely die out. Geometric study continued in the Byzantine Empire, too. You see it reflected sometimes in their art, like the amazing geometric mosaics in places like Ravenna. The source has a picture from the mausoleum of Galla Placidia.
It's quite a journey then, isn't it? From these initial sparks in Ionia, through the logical structuring by Euclid, the brilliant discoveries in Alexandria, and then the practical uses later on. If you had to sum up the big takeaway.
I think the core story is this incredible transformation. How the Greeks took what started as essentially practical measurement techniques and observations about the world and turned it into this profound theoretical science. They built this rigorous system based on logic and proof. And that system, that way of thinking, had just an immense lasting impact.
That really is the aha moment, isn't it? Seeing that leap from just measuring things to understanding the underlying principles, the why, through pure reason.
Exactly. And it connects right back to you listening now. Every time you think about a triangle or a circle or parallel lines, your understanding rests on this amazing foundation built by these ancient Greek thinkers. Those roots run deep.
So maybe a final thought for everyone to chew on. That Greek emphasis on abstract reasoning, on proof. How does that way of thinking still shape how we try to gain knowledge today? Not just in maths, but maybe in science, philosophy, even how we argue.
That's a great question.
Yeah.
And maybe, what other ways of thinking from the ancient world might still be quietly influencing us now in ways we don't even realize? Something to ponder.